This is the third video in a series of 7 about factoring, grouping. Here's an example of a factoring problem. We're going to use a technique called grouping. You'll see why they call it that in a minute. But first notice that we have 4 terms in this problem. Now you hopefully have seen the video prior to this, video 2, which was the GCF or greatest common factor video. And I'd like to approach this problem from a greatest common factor perspective first. So notice the coefficients of my variables here. Are they all divisible by some specific number? Well, some of them are divisible by 3 and some aren't. Some are divisible by 2 and some aren't. But there's no one single number that they're all divisible by, except 1, which we don't really count. And so we can't factor out a coefficient here. But how about the variables? Well, notice most terms have an x, but one of them doesn't. And so we can't factor out an x. There can't be an x in our GCF. And notice that some terms have a y and others don't, and so there's no y in the GCF. And the ultimate conclusion here is that there is no GCF. Technically we call the GCF 1. It wouldn't make much sense to factor out a 1. So it appears that we cannot apply the GCF method from the prior video to this problem. Now what we can do is something called grouping. Now this strategy, which I have yet to share with you, only works when you have 4 terms in the problem. It's very unique to that situation, which is rare. But notice this term does have 4 problems, so I'm going to consider grouping. Here's a bright idea somebody centuries ago came up with. They posed the question, what if we split the 4 terms into 2 pairs of 2 and tried to find a GCF only from the first pair? Well, if you look at the first pair of terms on the left here, both terms are divisible by 3. 6 and 15 are divisible by 3. And they're also both divisible by x to the first. In other words, x to the first is the lowest power. Therefore, I can factor out a 3x to the first from this pair of terms. Now notice I'm not factoring out a 3x from the entire problem, since I've split it into essentially the sum of 2 problems. So now to fill in the parentheses, just use guess and check. 3x times something would equal the thing above it. You'll eventually come up with this. If you didn't watch or need to re-watch the second video, the greatest common factor video, I would go back and do that at this point, if this portion of it is confusing to you. If it's not, moving on to the second pair of terms, the same question was asked. What would happen if we tried to factor a GCF out of the second pair? Well, if you look at the second pair of terms, 2 and 5 aren't divisible by anything in common, again other than 1. But notice there's a y in each term, and therefore I could factor out a y. And again the question becomes, how would I fill in the parentheses to make the bottom product equal to the top? Well, that too is guess and check. Eventually you'll come up with this. Pause the video if you need more time to think about that. Okay, so I had 4 terms. I split them into 2 pairs of 2. And something very useful has just happened, which is that the 2 quantities in the parentheses are exactly the same. Now, strangely, if you're doing your grouping problems right, this will always happen. If for some reason those don't match, take it as a sign that you've made a mistake. Now, beyond just the scope of a regular algebra class, technically those don't have to be the same. And if they weren't the same and you had done everything right, you would simply conclude that the 4-term polynomial is not factorable, and that would be the end of the problem. You would simply write not factorable, or prime, which is another word for that. But assuming that you're in an algebra course of some kind, which is what brought you to this video, you can assume that the person who chose your problems, your professor perhaps, or your teacher, has arranged the problem in such a way that it would be doable by grouping. Therefore, expect the two things in the parentheses to be the same. Okay, now before I go on with this problem, I have to take a brief diversion into factoring this problem. Imagine I had 3x times anything plus y times anything, where the anything could be a number or an algebra expression or literally any math object. Couldn't I, in this case, factor out the anything? And wouldn't that just leave me with 3x plus y here? And notice what's happening in this sort of made-up math problem is that I had an anything in each term, but when I factored it, I only wrote that anything once. That same logic that applied to that strange situation applies here, because I have 3x times something plus y times something. And I can simply factor out the something and get this. Now, in all my years of teaching, I've noticed that the typical student doesn't like that logic, and most students prefer a different explanation. So I'm going to share sort of a non-mathematical explanation with you, but it does work every time, and for some people that's good enough. So when you get to this stage and you notice, oh, I have the same thing twice here, and you will notice that. That will happen. When you see that, simply write it in one of the parentheses. It doesn't matter which one. And the two things that you factored out, the two GCFs from each individual pair, in this case the 3x and the y, just put those together to form the other factor. Now that's not very mathematical, but the great thing is it works every time. And like I said, for some students, the fact that it works and isn't real math doesn't matter. Gets you a right answer. Not my style, but it's a nice shortcut if you like it. Now I'm technically done with this problem, but I'd like to put our original problem back and just ponder one thought. If I have factored this 4-term polynomial into a product of two binomials, should it not be the case that if I were to multiply those two binomials out, I would get the original problem back? After all, that's what factoring is. So let's use FOIL, or any other method you like, to multiply our answer out and see if we do in fact get the original problem, which we should. All right, using the FOIL technique, first times first, outer times outer, inner times inner, and last times last, you'll notice we do in fact get an equivalent polynomial to the original problem. The terms are in a different order, but that doesn't make it a different polynomial. And that proves that this factorization is correct. And that concludes video 3 of 7.